Command injection is a critical vulnerability that allows attackers to run shell commands on a server, often leading to full system compromise. In this video we will explore how to identify and exploit blind command injection flows, which realistically speaking is the toughest and most common type of command injection one may come across during a pentest or bug-bounty engagement. We'll use free and open source tools like Commix and ffuf to target a web app with multiple injectable endpoints. Quick overview of the target app before we dive in. It's a Python Flask web app with several vulnerable endpoints running locally on port 5000. For example, the storage endpoint handles GET requests and reads the file URL parameter as user input. It then executes that input using Python's subprocess module in a shell command to simulate a command injection flow. After the first basic example, we'll replace the clean user input with a real command that incorporates it, creating a more realistic injection scenario. Because in real-world cases, it's extremely rare to find a parameter that just runs a command like whoami or ls just like that. Most injection points are embedded within larger commands requiring filter bypasses, character escaping, and careful error handling. There's also the create entry endpoint, which accepts post requests. It reads ID and file name from the request body, then unsafely includes file name in a shell command without any sanitization. We look at the session endpoint, which reads the session ID cookie value in post requests and executes it in a larger command, again without validation. The head endpoint accepts GET requests and reads the custom request header app key, which is then executed in an unsafe manner. And finally, we'll look at the orders endpoint, which reads and executes the path variable order ID. Here's a quick preview of the simple URL parameter blind command injection. As you see, there is no command injection indication in the server response, but if you look at the server logs on the right, you will notice that the command was executed, listing the contents of the application's root directory. Now let's bring Commix into the game. You can very quickly install Commix with apt if you are on Kali Linux, which I have already done, but you can also clone the project from the official GitHub repository. For our first example, we will attack the storage endpoint. We're running Commix with the -u option to specify the target URL. The -p flag tells Commix which parameter to attack, in this case, file. You can pass a comma-separated list here, or leave it out entirely to target all parameters present in the URL. I'm also using bats to skip user prompts and go with the default behavior. The OS CMD is set to whoami, so Commix will attempt to run that specific command. I'm adding skip heuristics to avoid the initial analysis phase because I like to live on the edge. The technique is set to T, which stands for time-based. Commix would try that eventually on its own, but I'm sort of cutting to the chase here. You can read about the available techniques in the project's wiki on GitHub. Finally, I've included ignore session, so previous results don't affect this run. Useful when you're testing the same target with different configuration. Let's run it and see what happens. As you can see, Commix detected and verified the vulnerable parameter. We can now run commands and retrieve the output in a time-based manner. Now that we have a basic understanding of how Commix detects and exploits command injections, let's move to a more realistic scenario. I replaced the user input variable with the global variable CMD that contains a short script. The replace function substitutes the user input placeholder with our injected command, which is then executed as a whole via the subprocess module as mentioned earlier. The script uses stats to create a file in the temp directory using the file parameter value as the file name, then appends a log entry, here sent to dev null, a device that discards all data. This could be any logging destination in a real system. At this point, the injection becomes much harder to detect. If we run the same command again, you will notice that it won't detect the injection this time, because our injected command is wrapped in double quotes. Luckily for us, bash strings wrapped in double quotes support features like variable interpolation and command substitution. For example, this syntax runs the whoami command in a subshell and inserts its output into the string, rather than printing it literally. This means that to exploit the injection now, we need to use command substitution syntax in our payloads or carefully close the existing double quotes, otherwise the injected command won't run. Let's explore one way to exploit this flaw using Commix, while also getting familiar with the prefix and suffix options. By setting the prefix to a $sign followed by an opening parenthesis and the suffix to a closing parenthesis, we wrap its payload injected by Commix in command substitution. This time it worked. You could get the same result by using the level option set to 3, which instructs Commix to perform more extensive testing on the target parameters. However, it's best to avoid heavy attacks when possible. Understanding how things work and making informed decisions is far more effective than gambling with tools. Let's now target the create entry endpoint, which accepts post requests. We'll use the same setup as before, including the prefix and suffix for command substitution. This time, we add the method option set to post and provide id equals 5 and filename equals test.txt as the request body. I've also removed the -p option to let Commix automatically test all provided parameters. Once again, Commix successfully identified and exploited the injection flaw. In a real black box scenario, where we might have discovered this endpoint through fuzzing tools like ffuf or GoBuster, we wouldn't know which request body parameters are valid. So instead, we could try a list of common parameter names that may be vulnerable to command injection. In this example, I'm using 25 common parameter names, which could scale to 100 or more, to fuzz the create entry endpoint for valid request body parameters while simultaneously checking for command injections. Let's see what happens. It took a bit longer, but Commix still identified the vulnerable parameter. Now let's switch tools and explore how to fuzz for potential command injections in header values using ffuf, a fast web discovery and fuzzing tool. We'll use 3 separate word lists, one for endpoints, one for header names to test, and one for payloads. As before, we'll focus on the time-based injection technique. We have a list of 5 directories or endpoints. The headers list includes the app key header name among other values, which, as mentioned earlier, is vulnerable to command injection specifically on the head endpoint. And for simplicity, we'll use a single, powerful payload to detect command injection, the slip command wrapped in command substitution. This works reliably across multiple contexts, whether the injection works cleanly out of the box, wrapped in double quotes, or executed in Linux shells like Bash or even PowerShell on Windows. The payload starts with a space on purpose to prevent the injected command from being concatenated with preceding text, which could otherwise break the command execution. The rest of the payloads are identical, except they use the IFS environment variable in place of spaces. This helps bypass filters that block or sanitize space characters on Unix systems, preventing execution from being disrupted. The final command is ffuf-u pointing to the target URL, the word fuzz, which is a placeholder that ffuf will replace with values from the word list directories.txt that I declared with -w. I did the same for the placeholders header and payload, parsing the word lists we saw earlier. I'm using the $H option to set custom headers and values, both coming from our lists with header names and payloads. In a real engagement, we would use much longer lists, possibly from the checklist project or asset node word lists. A very important detail, since we are trying to detect injections with a time-based technique, I'm using the filter time option set to less than 2,500 milliseconds to exclude responses with no noticeable delay. Remember, we configured the payload to sleep for 3 seconds. The final option, -C, simply preserves color in the output. Let's run it. As you see, we managed to detect the vulnerable endpoint and header name based on the response time as expected. We can also target cookie values that might be vulnerable to command injection. In this case, we'll omit the headers word list from the previous example and focus on the session ID cookie, which is vulnerable. I'm also using the -X option to set the request method to post, since the session test endpoint only accepts post requests. All 3 payloads were successfully executed and the vulnerable endpoint stands out. In modern web applications, where developers define dynamic routes instead of relying solely on static files, path variables are often used. If these variables are handled unsafely, they can also become vectors for command injection. We see that the orders endpoint reads the order ID path variable and handles it unsafely. To detect the injection, we'll use ffuf, this time combining a directory's word list with payloads to fuzz the second level path segment for possible injection points. Having identified and verified a command injection issue, you can either go for a reverse shell to dig deeper, potentially escalate privileges or exfiltrate sensitive data. You can also use enumeration tools for that. Commix, for example, has special options for extracting user and system info. You can use Commix-H for help and check the enumeration section. But let's grab a reverse shell. I'm gonna fire up Villain, a simple and effective C2 you can install via apt. Since we know the target OS is Linux, I'll generate a reverse shell command accordingly. To ensure it executes, we'll wrap it in command substitution syntax. Then we'll URL encode the payload to safely transmit it to the server. Finally, we'll inject it into the vulnerable file parameter of the storage endpoint. We got a shell. The tools we used offer many more options for detecting command injections and much more. There are also other techniques worth exploring. For instance, instead of relying on time-based detection, you could use an external collaborator server to trigger a DNS or HTTP request from the victim. I'll cover that approach in an upcoming video. If you found this useful, please like and share, or you can support me on GitHub. See you on the next video, be sharp and stay tuned.